An open cylindrical tank of water has a hole near the bottom. The radius of the tank is 52 centimeters. The hole is a circle of radius 1 centimeter. The water level gradually drops as water escapes through the hole. Over a certain 20-minute period, the height of the surface of the water is given by the formula h equals 10 minus t over 200 all squared, where h is the height of the surface of the water in centimeters as measured from the center of the hole. T is the time in seconds from a particular instant t equals 0. What is the height of the surface at time t equals 0? Well, to get the height at any time, we just plug the time in here. So if we plug 0 in here, we get 10 minus 0 over 200. Well, that's just 10. Then we have to square 10 to get 100 centimeters. So initially, the height of water is 100 centimeters. So h is a function of time. So we're just getting h at time 0. After how many seconds will the height of the surface be 64 centimeters? So after how many seconds will this distance be 64? So we plug 64 in for h and we solve for t. Now the easiest way to do this is just to get the square root of both sides. The square root of the left hand side will give us 10 minus t over 200. If we take the square root of 64, one value is plus 8. There is another value which is minus 8. But let's look at this case first. To solve this, we bring the 10 over, so we minus t over 200 equals minus 2. So t equals 200 times 2, which is 400. Now let's see what happens if we take the negative square root of 64, which is minus 8. We solve this equation, we get minus t over 200 equals minus 18, or t equals 200 times 18, which is 3600 seconds. T is in seconds. Now 3600 seconds is 1 hour. Now the problem with this solution is that this formula is only valid for a 20-minute period. So t can only run from 0 to 20 minutes. And in this situation, t is more than 20 minutes, it's 1 hour. So we ignore this solution. Our formula is invalid for values of t greater than 20. So t must be less than or equal to 20 minutes. 20 minutes is 1200 seconds. T has to be in seconds. Find the rate at which the volume of water in the tank is decreasing at the instant when the height is 64 centimeters. We are looking for the rate of change of volume of water. Now, with respect to what? Well, we're not actually told explicitly what we want the rate of change of volume with respect to. But implicit in this question is that we're getting the rate of change of volume of water in the tank with respect to time. In other words, we are interested in dV dt. Now to get dV dt, we need to see a formula for V. V is the volume of water. As you can see, the volume of water is in the shape of a cylinder. A cylinder has a fixed radius of 52 centimeters. However, the height of water is changing. We can see that h is decreasing with time. H is obviously a function of time given by this formula here. So if we want to get the volume of water in the tank at any time, we need this formula for the volume of a cylinder, which is pi r squared h, or pi r squared is the circular cross-section of water, r is the radius of the water, which is the same as the radius of the tank essentially. We ignore the thickness of the tank. H is the height of water in the tank. So pi times 52 squared is just a constant. In terms of pi, this is 2704 pi. H, however, is a function of time. So we could write V like this to emphasize that V is a function of time. It's just a constant 2704 pi times h, where h is a function of time. We want dV dt, as I mentioned earlier, so we have to differentiate this with respect to time. So the 2704 pi is just a number, it's just a constant, we leave it to one side, and we just differentiate h with respect to time. And that's how we get dV dt. Now, what is dH dt? Well, we know how h varies with time. We know that h is given by this formula here. So if we want to get dH dt, we have to differentiate this with respect to time. We use the chain rule here. We differentiate around the brackets, bring down to 2, subtract 1 from the power, so we get 2 times 10 minus t over 200 to the power of 1. Then we must multiply by the derivative of what's inside the bracket. Well, the derivative of 10 is 0 because 10 is just a constant. The derivative of minus t over 200 is just a coefficient of t, which is minus 1 over 200. So we can see that dh dt is a function of t. dh dt depends on what t is. So we want to find the value of t when the height is 64 centimeters. But that was covered in the previous part. When the height was 64 centimeters, then we found that t is 400. So when the height is 64 centimeters, t is 400. So we can get the dt at t equals 400. So we plug 400 in for t here. We get 400 divided by 200. That gives us 2. We've 10 minus 2 is 8. So inside the bracket we've 8. We've 8 over 200. 8 divides into 200 25 times. So we just have 2 times minus 1 over 25, or minus 2 over 25. So we plug minus 2 over 25 in for dh dt, and we'll then have dv dt. Actually, we'll have dv dt at t equals 400, which is the same thing as saying we have dv dt when h is 64. So this is given in terms of pi. Notice that we have a minus sign. dv dt is negative. Well, that's the case if our function is decreasing as time goes on. So v is decreasing. We can show it like this, just an arrow pointing down the way, as time increases. Of course, in all problems we deal with, t is increasing, of course. So if this is the case, dv dt will be negative. The volume is decreasing. If the volume was increasing, dv dt would be positive. Well, you see, dt is always positive, so the denominator of this derivative is always positive. However, if the volume is decreasing, then the change in the volume will be negative. So the volume after a certain interval of time will be less than what it was an instant dt earlier. So the change in the volume will be negative. So dv dt overall will be negative. Now we want our answer correct to the nearest centimeter cubed, and if we do that we get 680. The question actually asks us for the magnitude of the rate at which the volume of water in the tank is decreasing. dv dt is minus 680 centimeters cubed per second. As for the units, volume is in centimeters cubed because all the lengths are in centimeters. So we've centimeters cubed for dv, but time is in seconds. So we've centimeters cubed over seconds. So we can write it like this: centimeters cubed times s to the power minus 1. If we bring up the s, it becomes s to the power minus 1. The magnitude of this quantity is just plus 680 centimeters cubed per second. So at the instant when t is 400, or if you like when h is 64 centimeters, the volume is decreasing by 680 centimeters cubed per second. So if dv dt was constant, this would mean that every second the volume would decrease by 680 centimeters cubed. Of course, dv dt is not constant. In the next instant, this value will actually change. dv dt is a function of time. It's 2704 pi times dh dt, where h of t is given by this. So dv dt involves time. It varies with time. The rate at which the volume of water in the tank is decreasing is equal to the speed of the water coming out of the hole multiplied by the area of the hole. Okay, so we're interested in the rate at which the volume is decreasing. If we're talking about the rate at which a quantity is changing, we're talking about the derivative of the quantity with respect to time. Again, time isn't mentioned here, but it's implicit in this. So the rate at which the volume is changing is dv dt. Change in volume divided by the change in time, or the derivative of v with respect to time. And it's equal to the speed of the water. Now the small v stands for speed here. You could think of it as velocity, although technically speed and velocity are not exactly the same. velocity is a vector, whereas speed is the magnitude of the vector, but it doesn't matter too much here. The area of the hole is capital A. So we multiply the speed by the area of the hole. This formula kind of makes sense if you think about it. If we double little v, if we double the speed, then we double the rate at which the volume of water in the tank is decreasing. That kind of makes sense. If we double the area of the hole, we double dv dt as well. That makes sense. Find the speed at which the water is coming out of the hole at the instant when the height is 64 centimeters. In the previous part, we saw that when h is 64, dv dt is 216.32 pi centimeters cubed per second. Well, more accurately, it's actually minus. The value that's used for dv dt here is actually the magnitude of dv dt. dv dt is minus 216.32 pi. This should really say the magnitude of dv dt. To show a magnitude, we can put lines on either side, vertical lines on either side. But it's understood from the context that dv dt here refers to the magnitude of the rate of change of volume with respect to time. The area of the hole is pi r squared. We were given at the start of the question that the hole is a circle of radius 1. So we just multiply pi by 1 squared. And v is the speed of the water at this particular time. Time when h is 64 actually. As a matter of fact, we know the time from the previous part. We know that the time is 400 seconds, but that's not too relevant here. So we just divide across to get v. We get 216.32 centimeters per second. Notice that the units of v are distance over time. Speed is distance over time. Just to see the units, the magnitude of dv dt is in centimeters cubed per second. The magnitude of the area, well, the units for the area is centimeters squared. Centimeters cubed divided by centimeters squared is just centimeters. So we end up with centimeters per second, as we would expect to. Centimeters is just a distance. Distance over time is speed. Show that as t varies, the speed of the water coming out of the hole is a constant multiple of the square root of h. So we're going to use this formula to get the speed. So we have to divide across by a, where a is the area of the circular hole. The area of the circular hole is pi times 1 squared, which is pi. So v is dv dt divided by pi. However, v, the speed, is a positive quantity. Speed is normally positive. Well, it's actually always positive. It's the magnitude of the velocity, and the magnitude of a quantity is always positive. We also have that dv dt is negative. So to ensure that v is positive, we have to put a minus sign here. So we plug in for dv dt from the previous part. We had dv dt in terms of dh dt. Here is dh dt from part C. So simplifying dh dt and then plugging in, we have 2704 divided by 100. That's 27.04. And this minus sign and the minus sign in front of the 1 over pi cancel out. And you can see also, of course, that these pi's cancel out. Now this expression in here should be familiar. It's from the very start of the question. Go back to the very start, you'll see h given as a function of t. So this expression here must be the square root of h. And this is what we have to show. We have to show that the speed of the water v is a constant multiple of the square root of h. And the constant multiple is 27.04. The speed in centimeters per second of water coming out of a hole like this is known to be given by the formula v equals c times the square root of 1962h, where c is a constant that depends on certain features of the hole. Find correct to one decimal place the value of c for this hole. So we need to know values of h and v for a particular hole. Well, the relationship between v and h is given from the previous part. So we can just replace v with this here. Now we can take the square root sign over both factors of this product. So we'll have square root of 1962 times the square root of h. But there's a square root of h on the other side, so the square roots of h's cancel on both sides. And we get down to this equation. So from this equation we can solve for c. We just divide across, and to one decimal place we get 0.6.